This video is about Chapter 15, which deals with geometric constructions. There are three well-known classical compass and straightedge constructions that stood open for thousands of years before being resolved in the 1800s using algebra. The first of these problems on our list is that of duplicating the cube. In this problem, we start with just some given cube, and the idea is to use compass and straightedge to produce a cube, or rather maybe the face or even side length of another cube, a larger cube, whose volume is double that of the original cube. Okay, so the second larger cube should have a volume that is double that of the original cube. The next problem involves angles. So given any angle, the question is, well, can you take that angle and produce another angle, say this one, whose measure is 1/3 of the original angle? And then finally, we have this problem of squaring the circle, where one is presented with a circle of some given radius, and what you want to do is use compass and straightedge to produce a square with area that is exactly equal to the area of the original circle. So essentially the rules here are that we have to use compass and straightedge, and that the straightedge must be unmarked, meaning that we can't use the straightedge as any kind of measuring device. The only thing that can be done with it is to draw a line. So in this chapter, we're going to address two of the classical construction problems of antiquity, those being duplicating the cube and trisecting angles. So in order to address those problems, we need some algebraic tools, and the first thing on our list is this notion of a quadratic extension field. So we start with a field f that's contained in the set of real numbers, and an element little k in f whose square root is not in f. Then we can form this set, which we call f adjoin the square root of k, just as it's just the set of all things of the form a plus b times the square root of k, where a and b are in f. And that is a quadratic extension field of f. Now, we need to know some things about these quadratic extension fields. The first thing that's nice to know is that it is indeed a field that sits within the real numbers. And in order to show that is true, you use a method very similar to what you used back in section 3.1 to show that q adjoin the square root of 2 is a field. So in fact, this was exercise 39 in section 3.1, if you want to go back and look at that. Okay, the next thing that we would like to know about these quadratic extension fields is that when we express an element of one of those fields in the form a plus b times the root of k, that expression is a unique expression, meaning that there's not some other a and b in f that will give you the same element of this field. And then finally, in lemma 15.7, we have this result about polynomials. And before we talk about this, I want to correct an error here. This should read a minus b times the root of k, and not a times, or a minus the root of k. All right, so the result is this, that we start with a polynomial that has coefficients in f, and let's suppose it has a root in this extension field, and let's say the root is a plus b times the root of k. Then its sort of conjugate root, a minus b times the root of k, is also a root of the polynomial f of x that lives within our extension field. Okay, now that also is a result that you have proved more or less in the past. In fact, if you look back at exercise 18 of section 4.4, so it hasn't been too long since you've done this, what you did there is you showed that if you have an isomorphism from the complex numbers to itself, and that fixes rational numbers, that is, phi of a equals a when a is a rational number, then if you have a polynomial f of x with rational coefficients and r is a root of this f of x with rational coefficients, then phi of r is also a root. Okay, so what's going on here is you can think about the extension field f adjoin the root of k as playing the role of the complex numbers here. You can think of the base field f as playing the role of the rational numbers, and then the isomorphism phi is just the mapping that takes an a plus b times the root of k and sends it to a minus b times the root of k. Notice that when b is 0, that isomorphism just takes a to a. In other words, it fixes things in the base field. Okay, so in any case, if a plus b times the root of k is a root of this polynomial, then a minus b times the root of k must also be a root. Okay, the next result we need has to do with reducibility of certain polynomials. So here the setup is that we have two fields, f and k, where f sits within k. And we have these two polynomials, f and g, that both live in the polynomial ring with coefficients in f. And then we have this third polynomial, k, that lives sort of in this larger polynomial ring with coefficients in the larger field, capital K. And now we're supposing that we can take f and write it as a product of g times k. So it turns out that if you can write f as a product, g times k, then this polynomial k must have coefficients in f, not just coefficients in capital K, but coefficients in the smaller field f. Okay, and the proof is rather short and sort of interesting, so we can go ahead and write it down here. It relies chiefly on the division algorithm. So if we use the division algorithm in the polynomial ring over f, we can take our polynomial little f and write it as g times some h plus a remainder r, where h and r are polynomials with coefficients in f, right? F, remember, is a subfield of K. So this equation that we got from the division algorithm just a little bit ago, you can think about that equation as occurring in the polynomial ring with coefficients in capital K, right? Because F, G, H, and R all have coefficients in F, and F lives within K. Now, on the other hand, from our hypothesis, we have written, we know we're able to write f of x as g of x times k of x. That also is occurring in this polynomial ring. with coefficients in k. Now, you might remember that we have a division algorithm in this polynomial ring with coefficients in k, and that there's a uniqueness portion of that division algorithm. And what it essentially says is that in these two equations here, the h and the k have to be the same, and the r and the 0 have to be the same. But remember, this h was originally formed from the division algorithm occurring over the field f. And so h of x has coefficients in f. And therefore, k of x, because k is equal to h, k must also have coefficients in f. And that is what we had wanted to show. So it's completely reasonable to wonder how in the world this stuff about quadratic extension fields and reducibility of polynomials is connected to geometric constructions by compass and straightedge. So here over the next few slides, we're going to want to draw a connection now between compass and straightedge constructions and sort of more algebraic topics. Okay, our starting point here is with this notion of a constructible point. So to get a constructible point, well, that's going to be just a point in the plane that we can obtain from two given points, 0, 0, and 1, 0, using a series of compass and straightedge constructions. Now, this idea of using a series of compass and straightedge constructions, that seems rather vague, and it's made far more clear, I believe, in the textbook. But let me give you some sort of indication about what we mean by this series of compass and straightedge constructions. So let's start with our 2 points, 0, 0, and 1, 0. So there we have 0, 0. And here we have 1, 0. And what can we do with those points, with compass and straightedge? Well, one thing we can do is lay down our straightedge and draw a line that passes through those 2 points. So we can do that with our straightedge. And then with our compass, I could take a circle at center 0, 0. So my compass tip would go at 0, 0, and the pencil would go at 1, 0. And I could draw this circle around here, supposedly centered at 0, 0. And I could do the same thing with a circle centered at 1, 0, where the pencil is at 0, 0. Get a circle, I don't know, something like that. Now, you might notice that these figures that we've drawn, they intersect at certain places, right? Like here we have an intersection point at 2, 0, and here we have an intersection point at -1, 0. And up here and down there we have some intersection points. So the top intersection point is at point 1/2, root 3 over 2. Root 3 over 2. And so that's where that thing is. Okay, and then we have this one on the bottom where the y-coordinate is minus root 3 over 2. So those new things, those new points that we've created as intersections of the lines and circles, those are new constructible points. And we could make even more constructible points now from these given constructible points by, again, using our compass and straightedge to make more shapes and determine more intersections. For instance, the point 1/2, root 3 over 2 and the point 1/2, minus root 3 over 2, they can be joined by a line using our straightedge, and that makes a new constructible point right there on the x-axis whose coordinates would be 1/2, 0. Right? So in that way, we can form a whole lot of constructible points, as you can imagine. Now, for certain constructible points, that is, ones that lie on the x-axis, that is, are of the form r comma 0, we can form what are called constructible numbers just by peeling off the first coordinate of that constructible point on the x-axis. So in our picture that I've drawn here, we see some constructible numbers already, like -1 and 0 and 1/2 and 1 and 2 are the constructible numbers that are determined by the figure that I've drawn up to this point. So at any rate, that's the idea of constructible points and constructible numbers. And again, our goal is to try to connect these notions to the notions of quadratic extension fields and other such objects. So the first thing that we learn about constructible numbers is that we can add them, subtract them, multiply them, divide them, and take square roots and get new constructible numbers. Okay, so we can check some of these things in fairly short order just by drawing a few pictures. So, for instance, let's begin with looking at the product A times B. So, if A and B are constructible numbers, then I should be able to draw a figure like this, where I can construct that point at A, and because 1 is a constructible number, I can do a 1 there, and then maybe I have a B up here, which I can get because it's constructible. And now I lay my straight edge down, and I make a line there, joining 1 and A, and then then I can construct a parallel line up here that comes over and strikes this axis here at X. And we might see, using similar triangles, that 1 is to A as B is to X. And so that says that X should be equal to A times B. Okay, so that's just like a thumbnail sketch of why A times B should be constructible if both A and B are constructible. Okay, well, let's continue on with this theorem 15.1. And here on this slide, I want us to see why, or a thumbnail sketch at least, about why the square root of D ought to be a constructible number. So we know that, that D is constructible and 1 is constructible, and so their sum should be constructible, right? That's just by this first part of the theorem. So let's suppose this is 1, and this out here is D plus 1. Then what I do is I use my compass and straight edge to compute the bisector of that segment, or the midpoint. I find that point, and then I can use my compass with center at that midpoint and pencil at one of the endpoints to produce a semicircle, like this. And then, once again, I can use my compass and straight edge to erect a perpendicular from 1 that comes up and hits the circle at some point. And so now what I want to do is focus on the length of that segment X that joins 1 to this special point here up on the circle. So now I'll draw in a few more segments, that one and that one, using my straight edge. Now, this length here, I want you to remember, is D. Now, using similar triangles, I know that X is to D, that's using this triangle, is the same as 1 is to X. That's using this right triangle here. And so that says that this x squared is equal to d. And so then this length x that we've created using compass and straight edge is the square root of d. Okay, now remember earlier we said that constructible numbers come from constructible points of the form r comma 0. And so you might be wondering, how in the world do we take this point up here on the circle and translate it to a point that's on our horizontal axis? Well, what we could do is take our pencil or our compass center, put it at 1, put the pencil up here at this special point on the curve, and then draw a circle down to where it hits there on the x-axis. And then if we subtract 1 away from that particular point on the x-axis, move it to the left by 1 unit, then we, honest to goodness, do wind up with a point of the form root d comma 0, and then we just pick off, of course, the first coordinate, root d, to get our constructible number. Okay, now one of the corollaries of this theorem is that every single rational number is a constructible number, right? You can form the integers just by forming successive circles of radius 1 centered at various points on the horizontal axis. And then you can divide those integers using this third part of theorem 15.1. So we get all of the rational numbers as constructible numbers. And in fact, we get more, right? Because we get the square roots of constructible numbers being constructible. So the rational numbers is a proper subset of the constructible numbers. So as a follow-up to this, I think it's worth pointing out whether there are some other types of operations besides addition, multiplication, division, and root that will give us new constructible numbers. This actually turns out to be an exhaustive list, and the reason is that if you think about the equations that govern lines and circles, so lines are linear equations, circles are sort of quadratic objects, and now what we're doing when we can form these constructible points is we're looking at intersections of those. So you can imagine solving a system of equations that involves linear and quadratic equations. And the very most that you're going to get in terms of solving these equations is quadratic. And so at most you will expect at each step to pick up some square roots. Our next result is this theorem 15.6, which is a pretty important result. It draws a direct connection between constructible numbers and these quadratic field extensions that we were talking a little bit earlier. It essentially says that if you start with a constructible number, then you can produce a chain of quadratic extension fields where this constructible number lives within the largest of those fields. So instead of proving this theorem, I think what I want to do is show you a specific instance with a specific constructible number and a specific quadratic extension chain. So the number we're going to start with is this r, which is going to be 2 plus 3 times the root of 1 plus 7, or 1 plus the root of 7. And if you're going to argue to someone why that is a constructible number, you might start with the inside of this root and say to yourself, well, or say to this person you're talking to, that we know that 1 plus the root of 7 is constructible, and therefore when we take its root, we get another constructible number. And that leads to the fact that R is constructible. So how does that play out in terms of quadratic extension fields? Well, we start with our base field, which is the rational numbers, which we just call f sub 0. And the very first thing I want to add to f sub 0 in order to argue that R is constructible is this 1 plus the root of 7. But I can get that by taking this base field and adjoining to it the square root of 7. Right, so this is going to be my f1. It's a quadratic extension of f0, and it contains this number 1 plus, the root of 7, which I would use at the beginning of any argument that, that R is a constructible number. Okay, so now what do I need to add on to this new field f1? Well, now I need the root of 1 plus the root of 7, and so why don't we adjoin that on? So this is contained in f1, and now we're going to adjoin on the root of 1 plus the root of 7. And we're going to call that field f2. It's a quadratic extension of the previous field. And my number R, which is 2 plus 3 times the root of 1 plus the root of 7, sits within f2. And so here we have this, this chain of quadratic extensions. In this particular instance, n is equal to 2, and our constructible number sits within the largest of these fields. Now we come to the key result of this chapter. It's theorem 15.9. And what it says is that if you have a cubic polynomial with rational coefficients, but no rational roots, then in addition, this f of x can have no constructible numbers as roots. So the theorem says for cubic polynomials, no rational roots means also no constructible roots. Okay, so we're going to go through the proof of this theorem. The proof is by contradiction, and we're going to suppose that this we've got such an f of x, a cubic polynomial, with no rational roots, and we're going to suppose it actually does have a constructible root and see what goes wrong with that. So we know from the previous theorem that if it has a constructible root, then any root must sit within one of these quadratic extension chains. And what we're going to do is we're going to pick the shortest possible chain of quadratic extensions where there's a constructible root in the last member of the chain. So we're going to let R be this constructible root. And because f sub n is a quadratic extension of the previous field, we can write f sub n as f sub n minus 1 adjoin the root of k for some k in f sub n minus 1. And then we can write R as a plus b times the root of k for some a and b in f sub n minus 1. Now, one thing we need to note is that b cannot be 0, because if that were true, then R would be equal to a. And a lives in f sub n minus 1, and that would mean that there would be a shorter extension chain containing R. And that would be a contradiction. So b has to be non-zero. Now, we go back and look at lemma 15.7, and what it says is that because a plus b times the root of k is a root of this polynomial f, then so must a minus b times the root of k be a root of f. And so if we use the factor theorem, where here we're denoting a plus b times the root of k is equal to r, and r bar is a minus b times the root of k. The factor theorem then tells us that we can write f of x as these two linear factors times some other polynomial h of x, where here h of x is in the polynomial ring with coefficients in f sub n. But it turns out if you multiply together x minus r times x minus r bar, if you multiply that out, you can see actually that the resulting polynomial will have rational coefficients. And f of x also has rational coefficients. Therefore, we have this lemma 15.8, which says that the polynomial h must also, in addition, have rational coefficients. And because f is a cubic polynomial, and this product x minus r times x minus r bar is of degree 2, that means that h has to have degree 1. So that means h is a degree 1 polynomial with rational coefficients, and hence it must have a rational root. But if h has a rational root, then f must have a rational root. But that's impossible because we have assumed from the beginning that f has no rational root. And therefore, the theorem is proved. Okay, now what we want to do is sort of the fun stuff. We want to take this theorem 15.9 and use it to prove the impossibility of certain constructions. So, for instance, we can now show it's impossible to duplicate the cube. And I want you to remember that, of course we can't produce a cube in two-dimensional space, but in order to double the volume of a cube, and let's suppose the side length is of length 1, what would we have to do? Well, we'd have to produce a new cube where the faces of each of the squares are of length cube root of 2. And so in order to be able to duplicate the cube, you need to know that the cube root of 2 is a constructible number. So this r, cube root of 2, is a root of the polynomial x cubed minus 2, which is a cubic polynomial with rational coefficients. Now, if we apply the rational roots theorem, we see that the only possible roots of this cubic polynomial are plus and minus 2, and neither one of those works as a root of f of x. And therefore, this polynomial f of x has no rational roots. But then theorem 15.9 jumps in and says, well, then f of x has no constructible roots either. And therefore, this r, which is a root of that polynomial, cannot be constructible. And it follows then that duplicating the cube using these traditional compass and straight edge rules is impossible. Okay, next we're going to show that it is impossible to trisect a 60-degree angle using the traditional compass and straight edge rules. Now, a little figure that goes along with this that I think would be helpful is, let's suppose we have our 60-degree angle, and let's say we have the unit circle here, which we can construct. And let's suppose for a moment that we could trisect that 60-degree angle. Right, that we could, in other words, we could construct this 20-degree angle. Then that point on the unit circle would be a constructible point, and if you dropped a perpendicular down to the x-axis, you would get a point on the x-axis where the x-coordinate would be the cosine of 20 degrees. So if 20 degrees were constructible, by compass and straight edge, then the cosine of 20 degrees would have to be a constructible number. So that sort of explains the first sentence of the proof, that if 60 degrees could be trisected, then r equaling the cosine of 20 degrees would be a constructible number. Now here, to continue on with the proof, we need a trigonometric identity, which neither you nor I would probably remember. So it's this one that says the cosine of 3 times t is 4 times cosine cubed t minus 3 cosine t. And in fact, you'll be proving that identity in one of your exercises. So if you use that identity, and you use the fact that the cosine of 60 is 1/2, then what you find is that this number r, cosine of 20 degrees, has to be a root of this polynomial, 8x cubed minus 6x minus 1, that has integer coefficients. So again, just like in the previous problem about duplicating the cube, we now check for rational roots of this cubic polynomial. So the rational roots theorem tells us that there's a collection of 8 possible rational roots, and if you try them all, you find that none of them work, and therefore the polynomial has no rational roots. And then theorem 15.9 jumps in and says, well, that means that f of x has no constructible roots, and therefore this cosine of 20 degrees, which is a root of that polynomial, can't be constructible. And that means that trisecting the 60-degree angle is impossible.